This work is illustrated by traveling along the National Highway N623 between Santander and the port of El Escudo, which starts from the roundabout located to the south of the Marqués de Valdecilla Hospital. In a previous video, we have seen how information on the accident rate can improve safety by informing drivers of dangerous sections and indicating the specific dangers in the most significant places through which they pass. However, although this information is very valuable, it suffers from certain shortcomings and problems, which are intended to be solved with the methodology that will be explained in this video. More specifically, it is intended to solve the following problems. That the dangerousness of each part of the highway can be determined without the need for accidents have occurred in it, that is, evaluating, through a model, the probability of minor, serious and very serious accidents in that place. B. That the information on this local hazard be personalized and adapted to the specific circumstances in which it circulates, that is, taking into account the driver of each vehicle and its experience, the specific vehicle being driven, existing traffic congestion, the weather, whether you drive during the day or at night, etc. To do this, it is most convenient to reproduce the road and its main characteristics in a mathematical model, but taking into account that it is a random problem, since practically all the variables that intervene in it are. Before explaining what Bayesian networks are in detail and explaining how they are built for the specific case of roads, it will be shown how the problem has been solved, so that a prior idea of the information received by the driver about the risks he takes when driving on the road can be obtained. I am going to describe an application that we have developed, in the form of a web page, to determine the risks that are run at each point of a road. To define the road, it is traveled in a vehicle, placing a camera in the front and another in the back, so that the video recording does not have to be repeated on the way back. The video can then be analyzed in detail to identify the various elements that influence the safety of that road. In this way, a graph is generated in which all the signs that are found, the curves, the intersections, the roundabouts, the elevation changes, etc., are reproduced. Some elongated rectangular marks are also incorporated, such as those in the lower part of the figure, which indicate the speed limit sections, those in which overtaking is prohibited, those that correspond to curves, etc., etc. Finally, the kilometer points of the main elements, such as signs, road intersections, roundabouts, are included, etc. In this way, you have a simplified graphic representation of the road with which you can work. To make things easier, a drawing of a vehicle has been placed under the diagram in green color, which will move as the video progresses, indicating the position with greater precision from its front part. To facilitate visualization, the road has been divided into many parts, which we will call pages, whose length varies and changes from one to another, between 250 and 500 m each. In our case, the N623 road is traveled, starting at PK 152 in Santander to PK 93 in El Escudo, having used 166 pages, to which 166 diagrams and their corresponding 166 risk graphs correspond. These risk charts give the annual ENSIs. ENSI is an acronym, in English, for Expected Number of Severe Incidents, that is, expected number of serious annual incidents. Medium and minor incidents are weighted to convert them into equivalent serious incidents. Therefore, the numbers give the expected number of equivalent serious incidents that can be expected to occur in a year at each point and the cumulative numbers since the start of the road if the road is traveled. These curves consist of jumps or discontinuities and increasing inclined sections. The former correspond to points where there is a concentrated risk, which corresponds to places such as intersections, traffic lights, curves, etc., where accidents may occur locally. The second correspond to sections in which there is a risk, but specific places of occurrence cannot be located. High slopes of these sections indicate high risks, and low slopes, low risks. The longer these segments are, the more the accumulated risk will grow. These graphs make it possible to identify the most dangerous points on the road and to propose general improvement measures, based on the total risks of all users of the road in question. Note that the sections near Santander have much more traffic than those near the Porta del Escudo, so the risks refer to the total number of users and not to a specific user. This means that the different traffic intensities on each section have been taken into account. The video can be started by pressing the Start Trip button so that the road can be traveled virtually and can be stopped at any time with the Stop button. When driving, the vehicle in green moves between pages, jumping from right to left at each page change. Notice how turning the page automatically changes the page and hazard graphics at the top and the information at the bottom of the video timing, PKs and page numbers. You can also stop the video, change the instance of the video, the PK or the page number, and, pressing the corresponding buttons, all the information is modified to adapt to the new data. In addition, when starting the video again, the new selected part is already traversed. An example would be to select KM 100, in which we already know that there are a series of very dangerous curves, which are in an area already close to the Porta del Escudo, as we are going to see. Another way to move along the road is to click directly on any point on the slider, which immediately accesses the corresponding part. If you want to know in detail the exact values of the risks, you can hide the video by pressing the Hide Video button, so when it disappears, a table with all the information is revealed. This table gives the number of the item, its PK, the type of item, the corresponding node, and the annual ENSI due to said items and those accumulated since the beginning of the road. In this way, each section or page can be analyzed much better and the different items can be more precisely identified. This allows us to identify the most dangerous points, in order to take the pertinent corrective measures. Risk calculations have been made using a Bayesian network that reproduces each and every one of the road items with their corresponding variables. Since the number of variables is in the many thousands, the computation would take many days to complete if the full Bayesian network were used. For this reason, the network must be partitioned, divided into much smaller subnets, which can be done by incorporating a small part of the previous one and another small part of the next one into the subnet of each page, with which independent subnets are obtained on each page, which make calculations much easier and faster, reducing calculation time from many days to minutes. In addition to the calculation time, the necessary resources are reduced. However, the most important thing is that if the particular data of each driver and those corresponding to the moment of driving are incorporated into these subnets, they allow the risks to be personalized to each driver and to the conditions in which they drive, day or night, with good or bad weather, with a lot or a little traffic intensity, with one vehicle or another, considering the speed, etc. Therefore, the risk information could be incorporated into the cartographic information, so that each driver could have the Bayesian subnetwork of each page or section and be able to carry out personalized risk calculations associated with their specific driving conditions. In this way, each driver would be monitored, evaluating their corresponding risks and, if these are high, informing them of the situation and, where appropriate, the competent authorities so that the pertinent measures could be taken. This is the biggest novelty, which is, on the other hand, what interests drivers the most and what would make it possible to reduce accidents much more. Therefore, this application allows not only to assess the accident rate of a road from the point of view of the institutions, but also to personally inform each driver of the risks they run in each of the sections of the trips they make. Once the application has been presented and described and you already have an idea of its main elements, we proceed to explain, in detail, how the problem will be solved. Bayesian networks will be used, which are today the most efficient tools and suitable for tackling this problem. The networks consist of a set of variables, which are the ones involved in the problem, a graph, which reports the direct dependencies between these variables, and, finally, some tables of conditional probabilities of each variable. Given their parent variables, those on which they directly depend. This requires evaluating the probabilities of occurrence of events and frequencies associated with the different elements involved. An important feature to keep in mind is that it is a high-dimensional multidimensional problem, since many thousands of variables are involved. It should also be noted that there are software packages that allow, given a Bayesian network, to determine the probabilities of the desired events, and that this is calculated from very efficient and fast way. If the network is very large, the computing time increases exponentially with its size. Which means that if the Bayesian network of a very long road were inserted, the computer could take days to calculate. However, by partitioning the network, which is linear, this time can be greatly reduced without altering the results, but, for this, the network must be partitioned properly. How to do it will be explained later. Before developing a model to analyze the safety of a highway or road already in operation, it is advisable to go through it, observing it carefully and identifying all the elements that influence its safety and that, therefore, must be reproduced in the model. If the road is new, these elements must be identified with the help of the project plans and the visit to the land through which it will circulate. The process of building the Bayesian network of a road must be carried out with the intervention of various groups of experts, including statisticians, since many times the interpretation of the probabilities of different events that arise is not trivial and subject to interpretation errors. Furthermore, the learning of parameters from the data is quite delicate and should only be carried out by specialists. The concept of item is then introduced to facilitate the passage from the reality of the road or motorway to the probabilistic model that tries to reproduce it. Items are localized elements associated with specific places on the road where accidents may occur, such as pedestrian crossings, level crossings, traffic lights, roundabouts, curves, etc. Others, on the contrary, are associated with road sections and are reproduced through occurrence rates, depending on the length of the section. Examples of these are head-on collisions, run over by loose animals, pavement failures, hard shoulders, slope slippage, etc. The attached table shows many of the items included in the proposed model, where the meaning of the names is obvious, so it is easy to understand what each of them refers to. As can be seen, it includes a wide variety of elements, among which the most typical of a road can be identified. A series of variables are involved in the occurrence of incidents associated with each item, such as the state of attention or driver fatigue, speed, weather, type of vehicle, driver experience, etc. All of them will be analyzed below. After a detailed analysis and the previous experience of the authors with probabilistic safety analysis problems in nuclear power plants and railway lines, the following variables have been considered relevant for the case of roads. Since there are discrete variables, such as the type of incident, which is considered minor, serious or very serious, or continuous variables, such as speed, for example, it is necessary to decide how to combine them. Since the combination complicates things a lot, it has been decided to discretize the continuous variables, so that they all become discrete variables. D. Driver attention. Human error is of great importance in traffic safety, so it should not be forgotten. Therefore, the model includes random variables to reproduce the driver's fatigue and state of attention. T. Driver fatigue. Since the driver is subject to increasing fatigue with driving time, it is considered an important variable. SD. Driver's decision on speed. This variable represents the driver's action in cases where he must adjust the driving speed. The assumed values for this variable are correct, involuntary error, and voluntary error. DRI, type of driver. This variable refers to the quality of the driver and can take the following values: professional, experienced, normal, and novice. IT, traffic intensity. It takes the values light, medium, and high. VIS, visibility. This variable refers to the quality of the driver's visibility, and can take the following values: good, medium and poor. VT, type of vehicle. It takes the values: heavy vehicle, automobile and motorcycle. S, speed. It takes a list of values that depends on each place and must include the values significant of it. V, vehicle failure. It takes values: no failure, minor failure, medium failure and serious failure. P, pavement failure. This variable reproduces possible occurrences of incidents due to road deficiencies, such as potholes, shoulders, width of shoulders, lanes, etc. The values of this variable are no fault, minor fault, medium fault and serious fault. Collision. This variable represents collisions of vehicles traveling on the road in the same or opposite direction and can lead to major incidents, such as frontal or side collisions. Its values are no failure, minor failure, medium failure and serious failure. W, climate. The weather alters the driver's attention, the conditions and the evolution of fatigue, as well as the safety of the road and the environment. Its possible values are good weather, rain/storm, wind, fog, rain/ice. SS, semaphore state. This variable is represented with three possible values: free, stop announcement and stop. AS, driver's decision at a traffic light. Take the values: correct, involuntary erroneous and voluntary erroneous. DS, driver's decision at a signal. Take the values: right and wrong. TF, technical failure. Take the values: present and absent. I, incident. This variable includes all possible incidents that may occur along the highway at a segment location and has values: no incident, minor incident, medium incident, and major incident. A summary of all this is shown in the attached table. Once the variables to include in the model have been chosen, each item must be assigned which of them affect it. Next, an analysis of dependencies between variables must be carried out, which will define the qualitative structure of the Bayesian network through its acyclic graph. This qualitative structure already provides very valuable information. For example, only by using the acyclic graph, that is, without knowing the conditional probabilities, one can answer questions such as, if the values of certain variables of a set A are already known and one wishes to know the values of others of a set B, what variables provide new, non-redundant, information about B that is not already contained in A? This conditional independence property will later allow the Bayesian network to be partitioned into many very small ones with the consequent reduction in computational complexity. Once the variables are defined, the structure of the Bayesian network must be designed. Some of the component subnets associated with their different elements are described below. Initial Bayesian network. This Bayesian subnet reproduces the situation when a user starts driving and has 7 nodes or variables: the weather W, the type of vehicle VT, the type of driver DRI, the traffic intensity IT, the visibility conditions VIS, the attention of the driver D and speed S. This is illustrated in the figure, in which the green nodes of this network, with the names of the corresponding variables, are those grouped by a blue square with a dashed line, and the gray nodes are those of adjoining subnets. One-segment Bayesian subnetwork without signals. A Bayesian subnet associated with a segment without signals contains 12 nodes: weather W, vehicle type VT, driver type DRI, traffic intensity IT, visibility conditions VIS, driver attention D, speed S, the driver's decision on speed SD, the vehicle failure V, the pavement failure P, the collision variable CO and the incident variable I, as shown in the attached figure. Bayesian subnetwork associated with a localized incident. This subnet contains only one variable I, as illustrated in the figure. This structure represents cases where a concentrated incident may occur. Includes the following items: intersection, roundabout, tunnel and viaduct entrances and exits, overpasses and underpasses, side entrances and acceleration lanes. Bayesian subnetwork associated with a generic signal. This structure is used where some action subject to error is required, and corresponds to the items, yield and stop signs, level crossing, pedestrian crossing, speed limit signs, prohibition signs. This subnetwork contains 5 variables: the driver's attention D, the driver's decision on a signal DS, the speed S, the technical failure TF, and the incident variable I, as illustrated in the figure. Bayesian subnetwork associated with a semaphore. This structure is used for semaphores, where some error-prone decision is necessary. It includes the semaphore item and 6 variables: the driver's attention D, the driver's decision on the signal DS, the speed S, the technical failures TF, signal state SS, and the incident variable I, as shown in the figure. Bayesian subnetwork associated with an alert signal. This structure is used to reproduce the changes in attention due to alert signals. It includes the following items and variables: items, permanent warning signs, temporary warning signs, distracting warning signs such as billboards, etc., prohibition purposes. Variables, driver attention, D. This subnet contains a single node and is illustrated in the figure. Bayesian subnetwork associated with a change of parameters. This structure is used to reproduce the parameters of change of road, weather, or traffic characteristics, among others. It includes the following items: climate change, traffic intensity change, road quality change, and terrain change. Variables, none. The figure illustrates how the different subnets are integrated into the overall network. They include the 2 types of subnets: the subnets associated with segments without signals and the other subnets. Next, we must see how each of the items to be reproduced is represented in the Bayesian network. This implies analyzing which variables are associated with each of the items. In addition, it must also be decided how the variables of each item are represented graphically. The figure shows how the different subnets look once they are assembled into the general network, as well as the different colors used for the different types of nodes and how nodes of the same type that connect to each other are placed at the same height to facilitate your ID. Conditional probabilities and their closed formulas. This is another very relevant stage for the final result. In it, groups of specialists of different types with varied points of view must intervene in order to correctly quantify the conditional probabilities or the reasonable ranges of variation. Obtaining closed formulas greatly facilitates the implementation of the Bayesian network model in a computer, as well as sensitivity studies. The conditional probabilities of all the nodes will not be detailed, as it would be very long and tedious. However, we do spend some time on some particular cases. Collisions. Firstly, the figure shows the diagram that allows obtaining the formula for the probability of collision conditioned on its parent variables, which are type of vehicle, VT, traffic intensity, VIT, vehicle failure, visibility, VIS, driver's attention, D, and speed, S. So the indicated conditional probabilities must be defined for any combination of the conditioning variables. The figure illustrates how the formula that gives these conditional probabilities is obtained, that is, the need to consider all possible combinations. Pavement faults. Similarly, the pavement failure incident depends on the 6 variables indicated in the nodes, circles, of the figure, in which it is illustrated how to obtain the closed formula that gives these probabilities in its lower part. Traffic lights. The same happens in this figure, which gives the conditional probabilities for the semaphore variable, which depends on the 5 indicated variables. Curves. Finally, the case of curves and their corresponding incident is included, which depends on 4 variables: the driver's attention, D, the type of vehicle, VT, the weather, W, and the speed, S. It is not intended that the meaning be understood. The calculation of these probabilities is somewhat complex. Reducing complexity through partitions. As already indicated, the Bayesian networks of real cases lead to a very high number of variables, many thousands, so it is necessary to reduce the complexity of the calculations. otherwise, the memory and CPU requirements would exhaust the capacity of the computer. Therefore, if it is desired to be able to use the proposed method on networks of a certain importance, a solution to this problem must be found. To solve the problem, the Bayesian network is partitioned into a sequence of networks, subnets, as small as possible, without altering the results of the calculations. This is the goal of the idea described below. This figure shows a part of the acyclic graph of the Bayesian network of a road. To reduce complexity, we partition based on the conditional independence property, illustrated in the figure, where we see that the nodes in the set A2 are independent of the nodes in the set A11 given the nodes in A21, because any path starting from the set A11 and arriving at A2 must necessarily pass through the set A21 in the moral graph of the total set joined to that of its ancestors. Partitions are sought such that the nodes of one of them are independent of the nodes of the previous ones, given the nodes of a common part. This implies that the information about the nodes of any partition is contained in the added nodes of the previous ones. In this way, any probability of the initial network can be calculated using only small parts of it, which makes it much faster. Of course, the results are the same. The figure shows how the previous network can be partitioned into two subnets A and C, which contain common nodes, those of network B. Note that, in this way, the separator set, B, when matching parents with common children, becomes in a complete set, that is, all pairs of nodes are connected, as indicated. These partitions, in addition to allowing calculations to be carried out much more efficiently and quickly, since they would go from days to minutes, can be used for something much more important. Knowing a partition allows calculating the probabilities associated with its variables, even varying those of the others, so the risk for each driver can be individualized. It is enough to enter the data of the driver, of his vehicle, of the prevailing atmospheric weather, of the intensity of existing traffic, of whether it is day or night, and immediately calculate the risks. This is a very important advance, which is not within the reach of currently used methods. This means that the Bayesian subnetworks associated with each road can be sent to the passing vehicle, and the onboard computer can then calculate personalized risks and inform the driver where appropriate. This is a very remarkable advance, even for automated driving, which can use this information to make decisions. The most dangerous points of the N623 between Santander and the port of El Escudo are identified below, according to the results of the analyses of the proposed model. This figure shows us the N623 road between Santander and the port of El Escudo. In it are marked the 10 points of maximum risk, which result after our evaluations. This table gives these points ordered by risk, with their pk, the type of associated item and the corresponding ENSIs, that is, the number of annual equivalent serious incidents expected, considering the medium and minor ones with their corresponding weighting. It is curious to verify that the most dangerous of all is precisely the exit roundabout located to the south of the Marqués de Valdecilla Hospital, with an ENSI of 0.15, which is equivalent to a serious incident every 6 years. It is also interesting to verify that the other 9 are precisely curves, which are also concentrated in a few kilometers, since 4 of them are in the kilometer located between PK 110 and Park 111, 3 of them between Park 118 and 119, and 2 of them between Park 127 and 128. This can be easily verified on the map, where the observation of the indicated kilometers reveals the presence of these points. In the figures that follow, the orthophotos are presented, taken from Google Earth, the positions of each point on the plane and the aspect presented by the risk curves, measured in ENSIs, in the surroundings of those points, which gives us a very clear idea of the situation. These points have been carefully analyzed and measures have been suggested to reduce the corresponding risks, having economically valued what it entails in terms of cost, as well as the profitability of the implementation of these suggested measures, which is done by reassessing the risks after the indicated changes. It is curious to see that the profitability is very high, which is to be expected, since it acts directly on the points of greatest risk and not in a general way without distinctions of danger. It must also be said that profitability normally decreases as improvement actions are included that affect points with less risk. We do not give more details here, since this is not the objective of the work. Finally, it is indicated that the proposed methodology has been shown to be very interesting and efficient. Once implemented, it is generally relatively easy to extend to other roads and provides the necessary information for the institutions responsible for road safety and, also, for each of the drivers on each of their trips, whose risks are clearly different from one to another, as there are changing and very varied conditions that greatly affect safety. In short, this is the information that is transmitted to the vehicle's onboard computer, so that it can monitor the driver and inform him of the risks, especially when these exceed certain thresholds. And we are approaching the end of our trip, because the top of El Escudo is near. The ascent is pleasant and has much less risk than the descent. For this reason, the maximum speed is 90 km per hour, while the descent is much more limited. Acknowledgements. We want to expressly thank the support of José María Mazin, who, during his time as Minister of Public Works, supported us in our highway and railway safety projects, which otherwise would have had serious difficulties in being carried out. Also acknowledge the support of the Royal Academy of Engineering and the University of Cantabria. Also, the help received from Elena Mora.